All right, so as it's obvious, I was not able to make it. I will give you the details Monday when we meet. In any case, let me summarize or finish up the thing about stress strain. And if you don't have the ability to finish the homework for tomorrow, then that's fine. We'll take it later. But this is the last. This is homework H9, which is the thing that has the stress strain curve. Most of the stuff I'm going to put here, I mentioned in class, but since we haven't done problems on it in class and so on, I figure I better re-emphasize it, put it back, and I'm going to actually do one of the homework problems for you, the last one, which is the most difficult one. And you should, you should take a look at it carefully, because if you understand that one, then everything should be, well, most of the stuff it's used there. So first, let me summarize. Plane stress. Okay, the case of plane stress, we've already discussed. You have a material in which all the stresses are in one plane. That means there are no stresses in the z direction if we use z, this going out, but there are strains. Now the relationships are sigma x. You have these equations anyway, but I took some time this afternoon trying to write them down with the least level of complexity possible. When I say complexity, I should say in the most compact manner. So this is A times the Poisson's ratio. This is 0. This is symmetrical, so I'll just write this like this, and this is G. Okay? And that matrix multiplies the strain in the x direction, the strain in the y direction, and the shear strain. All right? Now, in plane stress, we do get strains in the z direction, and they are equal to minus Poisson's ratio divided by the modulus of elasticity, which this thing wrote darker so that you could see better. Let me try this other one. Yeah, better. Much better. So A times nu A G. Okay? Epsilon x, epsilon y, gamma xy. Okay? Sigma x, sigma y, tau xy. That's plane stress. Now, in this expression, G is known as the shear modulus and has the formula E divided by 2, 1 plus Poisson's ratio, which is nu. And the constant A, which I have written there, is equal to E divided by 1 minus Poisson's ratio squared. Okay? I'm going to go to the computer to check that everything is visible on the screen. Okay, looks fine to me. So that is plane stress. Now the inverse of plane stress is when we put on this side the strains and on that side the stresses. So if I do that, then we would have that epsilon x, epsilon y, and gamma xy is equal, and in this case we have sigma x, sigma y, and gamma xy. And this would be 1 over E. This works out to be minus nu over E. This is symmetrical, and then this is 1 over E. Okay? 0, 0, and 1 over G. So that is the inverse relation connecting stresses to strains. Before we had the relation connecting strains to stresses, okay? Now, when the material is very thick, then we make an idealization. We can still work in the plane, but we make the idealization that we refer to as plane strain. And plane strain has, we did in class also, but anyway, putting it in the simplest form, sigma x, sigma y, and tau xy relate to the strains. And I tried not to repeat my constants here, so I have d, e, d, 0, 0, and g. And that's symmetrical, of course. And then this here is epsilon x, epsilon y, and gamma xy. Okay? So if the situation is plane strain, this is the relation. In plane strain, in the z direction there is stress, no strain. And this is E with a hat times Poisson's ratio epsilon x plus epsilon y. And E with a hat is equal to E divided by 1 minus 2 nu divided by 1 plus nu. You will find these formulas in your notes already. Okay? The inverse relationship relating strains to stresses can be obtained simply by inverting this matrix. Okay? I don't think we need it in any particular problem, but for the sake of completeness, oh, wait a minute. The constant d is equal to E with a hat divided, the constant d is equal to E with the hat times 1 minus nu, and the constant E is equal to E with the hat times nu. Okay, I'm checking. Yep, everything is in there. All right, now I'm going to finish by putting the inverse relationships. As I said, I don't think that we ever use them in any particular problem, but for the sake of having the whole thing, now what we want to do is to have the inverse relationship. We have Ex, Ey, and gamma xy, and on the right side we have the stress sigma x, the stress sigma y, and the shear stress tau xy. This is under the condition of plane strain. The matrix now is constant F, G, F. All right? And the constant F has the form 1 minus Poisson's ratio divided by E with the hat 1 minus 2 nu, and the constant G is minus nu divided by E with the hat 1 minus 2 nu. All right? Plane strain. So those are the formula. That's the summary of the formulas for relating stress to strain and strain to stress in plane stress and in plane strain, and they are particular versions or particularizations of the overall three-dimensional problem. Now, with regards to rotations, strains, like stresses, are not scalar quantities. We cannot say the stress at this point is something and have it said everything. We now know that there is sigma x, sigma y, tau xy, tau z, etc. The same thing happened with the strains. Now, even if we simplify the situation to look in 2D, right? We know that, like, we may want to look at the reality at a different angle for various reasons. The same situation happened when we want to look at the strains. Now, one possibility is to say, I don't need to learn how to rotate strains because I can always go to stresses, rotate the stresses, and then go back to strains. That is true, but there are some problems in which it's really inconvenient to have to do that, and it makes thinking quite complicated. I've realized looking at at this homework that I'm going to do next. Now, I have two choices: either teach you the Morse circle for strains, which require certain modifications, or just simply limit to saying these are the equations for rotating strains and let's just use them directly. I opted for the fact that since we don't do this so much with strains and so on, maybe it's cleaner if I just put the equations. So the rotation of strains, it's done like this. You will notice the similarity, it's almost perfect with stresses. So the strain in the rotated axis x1, I'm calling x1 the rotation, is the strain in x plus the strain in y divided by 2 plus the strain in x minus the strain in y divided by 2 times the cosine of 2 theta plus gamma, the shear strain gamma xy divided by 2 times the sine of 2 theta. And the rotated shear strain gamma x1 y1 is equal to the negative of ex minus ey, the strain in x minus the strain in y divided by 2 times the sine of 2 theta plus gamma xy divided by 2 times the cosine of 2 theta. Okay? Those are the equations for rotating strains. So if I know the strains in x and in y and the shear strain in x in the xy element, in other words, if I know for an element oriented like this what is going on, then I can say that for an element oriented in an inclined direction, in which the inclined direction is an angle theta, then the strains will have whatever these expressions tell me they do. Okay? If you want to get the strain in y, then of course you have 90 more for the theta. But you can confirm yourself that the same relationship holds for stresses. Once you know one side, you can get the other one because the sum stays the same. Okay, now we are going to use these equations in the problem that I will solve for you next. Okay, for rotating. So please, well, you can always go back in the video, but internalize it. These are the x1, y1 axis, right? This is the x1, y1 axis, and this is the xy. So if we have them in the xy and we want them in the x1, y1, these are the equations connecting the two. Now, looking at the problems in the book, I realized that there are that there are these two very simple things that are asked. I mean, if you read the book, you would encounter them immediately, but sometimes you find the question, what is the change in volume? Okay? And I just make you aware of the fact that the change in volume divided by the volume proves to be epsilon x plus epsilon y plus epsilon z. Okay? That's one expression to know in order to answer what is the change in volume over the original volume for a particular problem. And the other one is that the change in thickness in a material, imagine again if you have a flat plate and you pull it, it's going to get thinner, right? So when you have plane stress, you have strain in the z direction. Now that means that the strain in the z direction by the thickness is actually the change in thickness. So this is change in thickness. Pretty much by definition, right? I have something thick, I pull it, there is a strain in the z direction. How much did the thickness change? Well, by definition, epsilon z times the original thickness, right? So now I have presented to you everything that is quantitative, or let's see, everything that is equations, relationships, etc., that you need to solve all of the problems that are in the homework or that you may encounter with regards to this topic in this class. Now, what I want to do to conclude this short video review or whatever lecture is to take a look at the last homework problem of the set number 9. It is 7.7.19. Now, the book has it with numbers, and I am going to let you substitute the numbers, and I am going to solve it here for you. Problem 7.7.19. I'm going to solve it for you using purely symbols, okay? The symbols make it, for me, dramatically less cumbersome, much less cumbersome than plugging in all the numbers. And you can always plug the numbers at the end, and you will see, because the answer is in the back of the book, that you get the answer that it's stated. Now, this is a beam that happens to be rectangular, and its sides, it is B in width and H in height. At this point, at the center of the beam, there is a P load that is applied inclined like that. And the angle that this P load makes with the vertical is, to use the notation of the book, alpha. Okay? Now, we can see that this P has two components. One component that is along the bar and one component that is perpendicular to the bar. The component that is along the bar will produce tension on this bar because it's pulled. The component that is perpendicular to the bar will produce shears and moments throughout this bar. Okay? So I will erase it, but I'm going to put it here and just say this is the same thing as having this plus this, where this one here to the right is equal to P times the sine of theta, of alpha, and this one which is down is P times the cosine of alpha. This one gives normal stresses only, sigma, and this one gives shear stresses and normal stresses due to bending, right? These ones are uniform and these ones are my over I type stresses, all right? So this is the situation that we encounter in this problem. Now, what is it that we know? Well, what we know is that someone went to the neutral axis, the center of the beam, and put a strain gauge. Now, a strain gauge is a filament it's actually a device that we use to measure strains. So all we need to know to do the problem is the fact that I have a measurement device here that allows me to know the strain in the direction of the horizontal axis. In reality, that strain gauge is really a filament in which current goes through, and as the filament gets extended due to the strain, let me take a second. Please try to read the book so you get these things, clearly reviewed. It's just language, but basically, if you have 2 points and you put a filament there, a wire, right? But the wire is attached to the structure. Now, when the structure deforms, for example, let's say it gets longer, that means that the wire, because it's attached to structure, also gets longer, so it gets stretched. Because of Poisson's ratio, the wire gets thinner, right? If it gets elongated. So it gets thinner. And when it gets thinner, the resistance to the current passing through the wire goes up. It's less of a pipe. And what we can do is we can measure the change in the resistance, and then we can correlate the change in the resistance to the pass of the electricity to the actual strain. That's how a strain gauge works. Now, what the problem says is that we have two strain gauges at this point. One strain gauge, of course the strain gauge is not really a point, but for the purposes of this problem, we think about them as being a point. Okay, a real strain gauge measures the strain on some gauge, that is, it has to have some distance. But in the idealized problem that we look at, we just simply have, I'm going to make a blown up version of that location around there. Here, larger, here is the neutral axis, here is a point, and basically what we are saying is that we are able to measure the strain horizontal, and that we are able to measure the strain at that point in some angle. The strain in the horizontal direction is EA, and the strain at an angle theta is EB. Okay, the book gives values for EA, for theta, and for EB. This is the beam. Okay? EA, or epsilon A, epsilon B, and theta are known, are given. Why are they given? Because I'm the one who went to the beam and I placed the strain gauge in the x direction. I placed this other strain gauge at an angle theta inclined. I connected them to my machine, and that's it, right? Now we put the load on the structure and we measure the strain EA. In fact, to keep the theta off the game, I'm just going to give the angle. In the book, this angle is 60 degrees, so let's keep that number there at least. So this is epsilon, this strain gauge measures the strain at in that direction, and this measures the strain at 60 degrees. What the book says is, I will give you the values of epsilon A and epsilon B, and on the basis of what you know about mechanics and what we've taught about stress-strain curves, I'd like you to tell me how big was the load P and what is the angle alpha. Okay? Now that is really an excellent problem in the fact that it puts it all together, right? You really have to have a good handle on all this stuff, right? In order to be able to think through that problem. Now, you don't need to be able to visualize the answer to start working, but let me say it again. I've measured the strain in A and the strain in B. I know the dimensions of the beam. I know the material that